I mean, all these computers are more showing the offer, it's not hard to go back to the one that left us. Who's up there, Kobe? I don't know, it's from all the four investors.
All right, there we go. Okay, so I'm just going to jump right into where we left off last time because there's kind of some review built in. But remember, we're doing a confidence interval and a linear regression for the slope of the regression line. And do you remember why we focus on the slope only, not necessarily the y-intercept? Although there are tests, lots and lots of tests for y-intercepts as well. But for our purposes, do you remember? Why do we focus on the slope?
So I feel like y-intercept isn't usually applicable in the problem.
Well, so these problems that you're going to get from me, from the College Board, blah, 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 you're correct. But why do we care about slope in the context of like these problems? What does the slope of the line tell us? Do you remember, Alex?
The association between like positive or negative.
Right. Or it's positive or negative, or not at all, right? Remember we talked about like if there's no association, if the two variables are not really correlated, then the slope is going to be close to what? 0, right? Remember that? Like you're going to scatter all over the place, so the regression line slope will be close to 0. If you do have a relationship, it'll be different than 0, either positive or negative. So that's why we're focusing just on the slope. Got it?
So we talked about normally approximately normally distributed, like
The residuals?
yeah,
the y values?
Does that tie into like what's the importance of the
Good question. We're gonna revisit, but we'll talk about it real fast. So guys, remember the conditions? What were the conditions for that we spent most of our time on last time? Liner. Do you remember that? And so to make sure that we meet those conditions, to make sure that this test or confidence interval is appropriate, those conditions have to be met. And basically, if you think about it, in order to run a hypothesis test,
Yeah, in order to run a hypothesis test.
Okay. In order to run a hypothesis test about the slope, this even goes back to like chapter 2 or 3 or whatever it was when we first started linear regression. It has to be meaningful to begin with. Like there has to be a linear relationship to begin with, or I should say, a linear relationship should make sense. Do you know what I'm saying? So if we have a linear relationship, remember we said, if I have like a scatter plot, let's pretend this is my regression line. But if I have a scatter plot, most of the points are going to be close to the line, and then some of them are going to be a little bit further away. But that condition basically says that for a given x value, if I focus in just on these points around that x value, most of them are close to the line, and only a few are like further away. In other words, if I focus on the distance in the y direction from the line, or like the residuals, they're going to be normally distributed. Most of them are going to be pretty small, some in the positive direction, some in the negative direction. You know what I mean? You will have some that are a little bit further away, but they won't occur as frequently. So if I were to look at these residuals, the distance from the line, and think of those values, like let's say -1, +1, -2, you know what I mean? And if I were to make a dot plot of the residuals along that x value, they would be close to 0, but they would be like approximately normal. Does that kind of make sense?
Yeah. I didn't think we were going to.
Huh?
I didn't think we were going to. It was
Nope, this is like the gist of what we talked about last time.
Can you go over line real quick?
Yep, we're gonna. All right, so Ready? Yep.
No, I wasn't.
Yeah, but I told you to watch the video.
No, I was on him.
Oh, okay.
No, I did not watch the video.
All right, so confidence interval. This is a confidence interval for the slope. We always start with, and I would get out your formula sheet. So we always start off with the general formula for a confidence interval: statistic plus or minus critical value times the standard deviation. So in this case, the statistic, we're talking about the slope of the regression line, right? So in this case, the statistic is the slope from the sample. Remember we talked about the difference between the Greek letters and the English, or whatever you want to call them, letters, like our typical alphabet that we're used to. The Greek letters are the parameters from the population. The regular letters are the statistics from the sample. So we're estimating beta, which is the slope of the population, with B, the slope of the sample. Plus or minus, our critical value is going to be a T star, and then this times the standard error of B. So remember, the standard error of B is that like crazy formula. If you flip to the second page in your formula sheet, all the way at the bottom, remember this like crazy formula? Sigma of B, or actually I can go all the way over to the end, but S of B is equal to S divided by S of X times the square root of n minus 1, right? So here's the thing. If you think back to when we did linear regression, we talked about degrees of freedom way back then, again, chapter 3, I think it was. But in this case, degrees of freedom are going to be given by n minus 2 instead of n minus 1. Does anyone happen to remember why we use n minus 2 instead of n minus 1, Nora? Two variables, correct, yeah. So two variables, so our degrees of freedom is n minus 2. Got it? All right. So if you think back to last time, we looked at that computer output, and I'll show you in a second what I mean. But there's a T value given in that computer output that's not your T star. That's the test statistic, the T test statistic, if you were to do a hypothesis test. And remember, our T test statistic and the corresponding T star for a confidence interval are two totally different numbers, totally different, never going to be the same. All right, so let's look at an example problem. So we actually looked at this data a whole bunch way back in whatever, chapter 3. So take a second and read this. Does this data kind of look familiar, this example problem? It is. It's exactly from then, yep. So we have the number of miles driven, and we have the price that the car was sold. And another important part that we probably need to go back to is that this was a random sample, right? That's going to come up. So there's our data. Who wants to put this into L1 and L2 and do a least squares regression and all that kind of stuff? Alex will do it. What a nice person. Except for I'm actually going to go off of this screen, and I'm going to tell you no one's really going to. It would take you a long time to do that, right? So guys, just like I said, I know. Just like it was kind of like a silly question. So just like last time, you're not going to really be inputting data. You're going to be given summary output, okay? And then you're going to have to use the summary output to answer the questions. So you have a bunch of graphs, and then you have this, computer output, let's call it. So you have to make sure you look at each graph. What are they giving me? They're giving me, this might be a little small. Can you see what this says? Residual. So this is a histogram of the residuals, right? This is what? It says miles driven and price. So this is what? The scatter plot with the actual LSRL, right? Yeah, that's like the graph in the middle, that's the original data. And then over here, this is the residual plot, right? So make sure you know exactly what each plot is actually like showing you, okay? So they're asking me to construct and interpret a 90% confidence interval for the slope of the population regression line. All right. So we have to find the 90% confidence interval. Notice we're defining our population parameter. Just like when we were talking about means or proportions, you have to make sure, look, it says like beta is the slope of the population regression line. The whole, or I should say the line relating every single, if you were to have every single truck and their price and their miles driven, right? It's the population regression slope. So this interval is called a T interval for the slope because T is the test statistic. And we're doing a confidence interval for a slope. Got it? So this goes back to the conditions, the linear conditions, right? So LINER, linear. You need to look at the original scatter plot, the raw data, if you have it. So they gave it to us, right? All the way up at the top, they gave us the original scatter plot. I know it's like teeny tiny, but does that look like we have a linear relationship? It does, yeah. Now, let's pretend I didn't have this. Let's pretend I only had like these two graphs at the bottom. Could I still check that condition? How could I check that condition? We say it again? Yeah, the second part. Yeah, sorry. I didn't know what you meant by second sentence. Yeah. Yeah. You could just check the residual plot. If the residual plot has random scatter, remember that tells you that the original scatter plot is approximately linear. Got it? All right. So independence. We only check this condition if we did an SRS, right? So if we have an experiment where we randomly split the cars or whatever into two groups, we wouldn't check this. We would say, because we split, randomly allocated our two groups, we don't need to check this. We have independence. But in this case, we didn't do that. So we check the 10% condition. Got it? Okay. N, normal, but remember, that's kind of like what I was drawing over on the board over here. The residuals have to be normally distributed around the regression line. So we want to look at the residuals themselves. So here's my residual plot, remember? Now, does that really look normal? No, but if you think back to when we did a t-test in, chapter, I think it's 10 and 11, when we even just looked at like raw data, as long as our sample size is big enough, we can assume normality, right? So our sample size here is only 16. This is clearly not normal, but we are more checking for strong skews or strong outliers. So do we have any strong skews? Do we have any outliers? I would say no. So because we don't have any strong skews or strong outliers, I definitely wouldn't say that that looks normal, but I would say that probably the condition is met. Or you could even say, I might have some concern about this condition, but remember, if you're told to do a confidence interval or if you're told to do a hypothesis test, do you ever just say, I'm not doing it because blah, blah, blah? No. Okay, got it? Yeah.
So, is that all you would talk about, or if if it was normal, would you put it as normal? If the sample size was big, would you put it?
So be careful about saying normal.
Or approximately?
Yeah, you would say even approximately normal, unless you've checked. Really, we're looking for like symmetry. You know what I'm saying? And so even when you think about it that way, this is pretty symmetric. It doesn't have that like normality shape. But remember, this is all about like the sampling distribution. If we can probably assume, because we don't have any crazy you know, bimodals or like peaks, you know, like in weird places, like strong skews, that probably the sampling distribution is going to be approximately normal. Does that make sense?
Yeah.
Yeah.
So if we didn't get the histogram provided, how would we check the condition?
You have to, you're going to have it
So are we gonna have the histogram?
for the residuals.
Okay.
So
And you can make it.
yeah, you can make it in the calculator,
So
but that's if
It's just
you,
that we're not-
yeah, if you have to type in the data by hand, you could come up with a histogram of the residuals. And if you want me to review how to do that, I'm happy to do it. We'll go through these examples first, and then I'm happy to show you. But yeah, you could. Yeah.
You know how you were saying like, what was it? If it tells you to do a hypothesis test or confidence interval, you have to do it, even if you have concerns about it. Will you get points off if you don't say you have concerns about it?
Good question. I mean, I think, listen, if you were to have an example like this where the residual plot, or the histogram, I'm sorry, not residual plot, where the histogram of the residuals was like this, and then you have like an outlier. If it's something like so extreme, I would probably say, yeah, you better mention that that doesn't look good. You know what I mean?
Yeah.
But if it's something like this, where this one's not great, but it's not bad either, I don't think you need to mention it.
Okay.
Does that answer your question?
Yeah.
Yeah, go ahead. All right, guys. Anything else right now? Okay. So LINE is equal standard deviation of the residual. So remember, we check the residual plot. We want the residual plot to be like equally scattered above and below that line, y equals 0, which is really the least squares regression line, right? Does that look pretty good? Yep. And then we need our sample to either be an SRS, or we need, if we did an experiment, we need the experiment, the subjects randomly assigned. Yep, perfect. So all the conditions are met. Good? Okay. So now, because the conditions are met, remember I told you last time, this is honestly the hardest part, is the conditions. So now, because the conditions are met, we're going to use the output that they gave us. We're going to use this, right? We don't ever actually have to type in all the miles and all the prices into our calculator. We're going to use this, but you are going to have to do a little bit of math. So let me show you. Degrees of freedom, we said, is n minus 2. There were 16 trucks, data collected on 16 trucks, right? So do you guys see this? Degrees of freedom is 14. You with me? All right, so a confidence interval is the statistic. If I look over here, where's the statistic? Where's the slope? Yeah, that's this thing right here. So this is B plus or minus T star. Do they give me T star here? No. Remember, you're going to be given a T. Remember that little warning that was up a couple minutes ago? But this is not your T star. This is your test statistic. We'll get to that in just a second, all right? So we're going to have to look up T star just like we have before. So if you look at your formula sheet, flip over to the T table. This is a 90% confidence interval, right? So you can look at 90% confidence interval on the bottom, 14 degrees of freedom. So look down, 14 degrees of freedom. What'd you get? Right, 1.761. So that's how we get that T star. Got it? You will have to look that up. You can. If you use T, is it inverse T?
Yeah,
Inverse T?
But
Yeah.
you have to, it accumulates from the left. I made that mistake on my quiz and I got.
I always tell people, it's
accumulates
always
from the left.
easier to use this table. This table is super easy to use, I think.
You have to do 1 minus the
Right.
C level and then divide by 2. And then put that in. So it's a lot.
All right, so it's our statistic plus or minus the t-star times the standard error. Guys, do you remember we said they give you the standard error on here? That's what SE is. So this is your standard error. So do you see how we piece together this formula right here? Take a look at that. Do you see how we piece together that formula? Where everything came from? Now here's the thing. Because you didn't type the raw data into the calculator, you can't use like the test in there. Do you understand what I'm saying? You can't go like stat, test. So you're gonna have to manually type this part in. So you have to do this calculation. In your calculator, you're gonna type in 1.761 times 0.030, da da da, right? You got this, and then you add and subtract it from the slope. So you have to manually type this in. Is that clear? Okay. All right, I'll pause for a second.
Then you have to go both directions.
You do have to go both directions, yep.
I would just go one direction. But
No, remember it's a confidence interval, so you want like a maximum and like a minimum, you know, of your interval. Question?
What are we typing now? What's it called?
Remember, you can't use like a statistic, there's no statistical test. You can if you enter all the data to begin with. But I'm gonna tell you right now, like tomorrow when you take your quiz, I'm only gonna give you 10 minutes. It's gonna take you 10 minutes just to type that
So
in.
we got type like,
Yeah, just into the home screen.
like,
You have to type this in to come up with this. You understand what I'm saying?
yeah.
Okay. So anytime I create a confidence interval, I have to then, what? Interpret it, right? So the interpretation, we're 90% confident that that interval from, you know, those two numbers captures the slope of the population regression line. Make sure you're talking about it being a slope and coming from the population, and it has to be in context. So the population regression line relating the price of the price to the number of miles driven for these trucks. Got it? Yeah.
Only thing, the beginning you make me say like the true mean and the true proportion. We have to say that.
You could say the true population regression line. That's kind of like what population means there, you know? Good? All right, so that's a confidence interval. You ready for a test? Oh, if you were to enter your data into your calculator, what you would do is enter, you know, the miles driven into L1, the prices into L2, and you could, like Doug was saying before, like you could use the Linreg T interval, and then it spits out this. But again, you know, timing, it just doesn't make sense. They're always going to give you that output in some form that you will never have to do this for this interval and test in particular. For the other ones, you might have to enter in your data. Got it?
Yeah.
Okay. All right, that's basically what that says, I think. Yeah. Okay, now the hypothesis test. So again, if you want to flip back to the front of the formula sheet, your general formula is always there, your standardized test statistic. Statistic minus parameter divided by standard deviation of the statistic, right? So you have to like build this formula. You have to remember that it's a T and not a Z. And here's what it's going to look like. So it's T is equal to, the statistic is the slope from the sample, so B, right? Minus the hypothesized slope, which we'll talk in a second. It's, for our purposes, most of the time going to be 0, but we'll talk about why in a second. And then to divide it by the standard error of B. Degrees of freedom is n minus 2, just like before. And the standard error of B is the same place on the formula sheet. Cool? Let's jump in and look at an example. I don't think we looked at this data ever, so this might be totally new. So take a minute and read this. Kind of interesting. Who said that?
That's what I didn't try out.
Oh, you did it? I'm shocked.
I just want to know.
I just kinda got sad if I didn't cry.
Snapping rubber bands on the soles of it.
I know. It's not gonna kill them. They're fine.
If it's like a, like, you would put like this foot. We'll give them 20 lashes.
All right, ready? So we have the cry count. In other words, how many peaks there were in the most active 20 seconds of their crying, and then their IQ later on in life. Got it? All right. So again, let me go back a second. You can type all that data into L1 and L2. I'm not telling you that you can't, but I'm telling you that time is always going to be an issue. If you do it, you're going to probably run out of time, you know? So instead, they're going to give you something that looks like this. So here's some computer output from a least squares regression. Do the data provide convincing evidence at alpha equals 0.05 level of a positive linear relationship between count of crying peaks and IQ in the population of infants? So guys, what does that mean? A positive linear relationship. What does that kind of tell us? That's our
Slow.
correct, but yeah, so what, give me more.
I guess our R value, if it's a high R value.
Well, okay, there are hypothesis tests for the correlation coefficient, but we're not doing that. We're just dealing with slope. In real life, statisticians will deal with like that kind of stuff too, but yeah.
This slope tells us if it's a positive relationship, their relationship or linear.
Yeah, so we're saying that the slope, like, this is giving us our hypothesis, guys, that the slope is going to be what? We want to test to see that the slope is positive, right? So if we start like we always do, our HO and HA, notice this hypothesis test is about a population slope. So in my hypotheses, what symbol am I using here? Beta. So listen, it's not like a trick, like I just kind of swoop up and make a B like that, that's how I make my beta. But if you just do a capital letter B, do you think you're going to lose credit? Yes, you will. So it's beta. Yes. Yes, you have to use, just like, listen, what's the symbol for a population mean? Mu. So if you wrote HO, if you were doing a test for means and you wrote N is equal to 7, I would take a point off. No, stop it. Stop it.
There's no like B in statistics. Or is there? Capital B.
We just made a B.
All right, listen, come on, let's keep going. Let's go through this. Guys, come on. So HO is that beta is equal to 0. HI is that beta is greater than 0. We're defining what beta means. Beta is the slope of the regression line relating the IQ score to the cry counts in all infants, right? Alpha, they told me to use 0.05, so that's just kind of like our setup, right? So the test name is a t-test for slope. Next thing we check are conditions, so, right, like liner, right? So L, linear. I didn't go back and look at these yet, but let's talk about these graphs real fast. What's this first one on the left? That's just the raw data. It says count of crying peaks and IQ, right? This one is the one in the middle. Residual plot. Histogram of the residuals, right? So linear, you can prove it two ways. You can say, or you demonstrate it. I shouldn't say prove. So the scatter plot looks as though you have a positive relationship, or the residual plot looks like it doesn't have really any pattern to it. Independent, was this, and I can go back a second, which situation was this in terms of independence? So you have to, let me ask this, do you have to check the 10% condition?
This is a SRS, so yes.
Did you guys hear that? It's an SRS, so yeah, right? All right, so we would check the 10% condition. We have, I forget how many, there were 38 babies, I guess, so 38 is definitely less than 10% of all children, right? And then N, How about that residual plot of the, I'm sorry, the histogram of the residuals? It looks symmetric. Be careful, don't say it's approximately normal, because unless you check the 68, 95, 99.7 rule, you can't say it's approximately normal. You say it looks pretty symmetric. It maybe does have an outlier, but is it like crazy extreme? No, so I think it's pretty good. Equal standard deviation. We check. Go ahead, Alex. Go ahead.
I question equal standard deviation. Isn't that like that E in the liner? Isn't the same as the L kind of? Because you're saying that there's no like pattern in the residual plot.
No. So equal standard deviation. Here's what would not make this met, but would make the linear condition met. Ready? If you have, I'm gonna try and draw this. And by the way, we've been talking a lot about positive relationships. This all goes for negative relationships too. So I'm gonna just use a negative one as a for example. So all right, kind of bear with me. But if this is my least squares regression line, and this is like the data. You follow? Is it linear? As one increases, is the other decreasing? Yeah. But when I make my residual plot, do I have equal standard deviation? So my residual plot will look like this. Remember, if it has that, like, I don't know what you want to call it, where it like, yeah, like a cone shape, yeah, then that's not met. Do you get what I'm saying? So you have to have both things. And then random, we said it's a random sample 38 infants. Good? Okay. That was a good question though, Alex. Thank you. All right. Oh, I'm going the wrong way. Sorry. All right, here we go. So our test statistic. So we need T is equal to, here's our formula, slope minus the hypothesized slope divided by the standard error of the slope. Got it? The hypothesized slope was what? 0, right? Now listen, a lot of times when we in AP do these tests, we're going to say, is there a positive relationship? Is there a negative relationship? Or is there a relationship? If I just say, is there a relationship, what's my HA going to be? Not equal to. You know what I'm saying? Yeah, so a lot of times it's just your hypothesized slope is going to be 0. But in real life, could it be something different? I could say, is there evidence that the slope is greater than 3? You know what I mean? And this would be 3. Do you follow? But most of the time, for our purposes, it is going to be 0. So the slope, where do I get the slope from? Up here, there's your slope, right? Minus 0, and the standard error of the slope is that. You see where we got that? And double check on your calculator if you want to, but this divided by this is 3.07. You could either do that by hand real quick, or what do you notice? Yeah, the T, this is your test statistic, your T test statistic. They give you that, okay? So it's equal to 3.07. Do you still have to write this formula? You do. You still have to write that formula. What else did they give you? Yeah.
I noticed that the degrees of freedom aren't written up there, so what does...
Ooh, we should have degrees of, oh, you know what? It's teeny tiny.
But you do have to include that.
You do have to have, yeah, you do have to have degrees of freedom. Degrees of freedom aren't written anywhere up here, but yeah, I probably should have written it a little bigger for you. It's 36, right? So it's 34. So your degrees of freedom is 34.
No, I thought you had was 36. It was 38.
Oh, was it 38? I literally can't even read that. Thank you. You have a good memory. So degrees of freedom is 36. Good? Okay. So, yeah, so your p-value, listen to me carefully. This p-value on this table always assumes that you wanted to do a two-tailed test. So this p-value would be the p-value for a two-tailed test. Are we doing a two-tailed test? We're doing a one-tailed test. So what do I do with the p-value? Divide it by 2. So my p-value is 0.002. Does that make sense? All right. So the picture that would kind of go along with this, I know this is very small, I'm sorry, but this is a 0. This says t is equal to 3.07. This is shaded, and then this says p-value equals 0.002 right here, okay? But so this is what your picture would look like. So what would your conclusion be? What's your conclusion? Why? So some of us have not been really good about writing this whole thing. Why do we reject HO though? You need to tell me why. No, it's not assume anything. Why are we rejecting HO? Because P is less than alpha. You need to specifically state that. So our p-value is less than our alpha, so we're rejecting HO and say that there is evidence of a positive linear relationship between the count of crime peaks and then the IQ in all infants, or in the population of infants, or something along those lines. When do we say assuming HO is true? When we're interpreting the p-value. If we wanted to interpret the p-value, we would say, ready? Guys, stop. Stop. Our p-value, if I ask you to interpret the p-value, this is your p-value, 0.002. What is that p-value? It's assuming that what? So in the context, you would say, assuming that the...
There's no relationship between the IQ and the baby's cry.
Yeah, but let's be more specific than that. Don't just say there's no relationship. Assuming that the... Alec, go ahead. Yeah, assuming that the slope of the population regression line is 0, there's a 0.002, or I should say a 0.2% chance that you would get a sample slope equal to 1.4929 or greater.
Hi, Rick. We have an important announcement to make. We're finishing Mini-Thon and hosting our 4th annual Mini-Thon event.
Guys, questions? I'm going to stop this recording real fast so this isn't in here. But that's really it. Again, you can do this on the calculator, but you're not really going to. All right? Hold on. I'm just going to stop.